Okay, well, I think we should probably make a start now. It's a couple of minutes after I guess 3 o'clock in the Central Time Zone. Welcome to the second of our Athena X-ray Advances webinars. Today our speaker is François Mernier, and as you can hopefully all see his slides. So before we get started, just to remind everybody that you can submit questions at any time. You should see the Q&A button along the bottom of your Zoom. And we also have the Athena community Slack with a channel for the webinars. So you can also put questions there, and you can carry on putting questions there if you have any after the talk as well. And we can try to make sure that François sees them. Our speaker today is François Mernier, and as you can see from the slides, he's currently a research fellow at ASST. François did his PhD at Leiden and Esron, and he's also worked as a postdoc in Hungary. So according to his very nicely designed website, he also has interests in music and sports, but we've invited him here to speak to us today because he is an expert in studying the chemical history of the universe, and in particular how it's traced by X-rays. So at this point, I will hand over to François to tell you a bit more about this topic.
Thank you very much, Judith. Good afternoon, everyone, or good morning, or good evening, depending on where you are. Yes, and thank you very much for joining today. So for giving me the opportunity to give this webinar today. So we're going to talk a bit about the chemical history of galaxy clusters and I would say just the universe in general. So first of all, I would like to apologize in advance because you might hear me coughing quite a lot. I just recovered from a bad cold and I have some asthma, but I will try to do my best and not cough too much. All right, so I think we can quickly start. So just as a brief outline, I think it's quite important first to explain you, to give a good introduction on the topic, and then we're going to go through the main topic of this talk, which are actually 4 essential questions that we are tackling right now about chemical enrichment in galaxy clusters, in galaxy groups, in the universe in general. Of course, we're going to talk about future missions and Athena in particular, and then I will conclude. So let's just first start with an introduction. And as you probably know, one of the most interesting and the major question in astrophysics is, where do chemical elements come from? And well, to this question we already have quite a good answer actually. And we know that after a few minutes after the Big Bang, the universe was made mainly of hydrogen and helium. So 75% hydrogen, 25% of helium, with a little bit of traces of lithium and barium as well. But actually what you can see from this plot is that, of course, all metals are missing. So what I call metals is, of course, all these elements which are heavier than helium. So the question is, where do metals actually come from? And the short answer here is that they come from stars and supernovae. And I'm going to extend that a little bit further and explain you 4 main sources of enrichment, which might be relevant. Especially 3 of them will be relevant for this talk. So the first one is what we call core collapse supernovae. So these are, like the supernovae you can think of mainly when you have a massive star that just explodes. And so what happens is that at the when the massive star runs out of hydrogen, it starts to burn helium and then carbon, then neon, etc. So you just have like different layers of burning material down to iron in the core. And this process happens quite fast because, of course, we are talking about massive stars. And so this massive star at some point just explodes, releases its upper layers into the surroundings, also forming new elements during the explosion itself. And mostly what happens is that the iron core remains collapsing and just ends up in a neutron star or black hole. So basically, this core collapse supernovae produce mostly, I would say, alpha elements, so mostly oxygen, neon, magnesium, silicon as well, etc. And one of the interesting questions we can ask to ourselves is how much of these elements are actually produced per supernova, per per core collapse supernova. And this depends mainly on 2 parameters. So the first one is the mass of the star. And so if you think of not only one massive star in particular, but an entire population of massive stars, You can think of it as the stellar initial mass function. And second, the initial metallicity of the star. So namely, whether the star was previously enriched by a previous population of stars before. And this plot summarizes a little bit what you can expect theoretically from what we call the abundance yields. So just like how many of these elements are produced. So what you see on the y-axis is just the abundance normalized over iron ratio. So you see that iron is here set to 1. And you have just different models, different nucleosynthesis models. And in each of them, you know, for example, you can vary the initial metallicity, or you can just vary the IMF that you consider. And you see that for each of these models, you just have different predictions, different ratios actually, which is kind of interesting because it means that if, for example, you can observe one given core collapse supernova, and if you can observe its abundance and constrain its abundances in really good details, then you will be able to say something about its progenitor. So whether, you know, like what is its initial metallicity, its initial mass, and so on and so on. The second source of enrichment is type 1a supernovae. So type 1a supernovae are a little bit different because now we don't talk about massive stars anymore, but we talk about low mass stars, and particularly a binary system in which we have at least one white dwarf. What is not really clear is whether this white dwarf just accretes material from a main sequence companion, or whether you know, type 1a is a result of the merging between two white dwarfs. So this is namely either the single degenerates scenario or the double degenerate scenario. We are still not really sure about the real nature of this progenitor, but what we know is that type 1a should produce silicon, sulfur, argon, calcium, iron, nickel. So essentially elements from the iron, so-called iron peak. And of course, we're talking about low mass stars, so the time delay between this typical star formation and type 1 explosion should be longer than what we expect from a core collapse supernovae. So how much of these elements are produced? Here again, well, this depends first on the nature of the progenitor, so what I mentioned with a single degenerate versus double degenerate scenario, but also on the physics of the explosion, in the sense that we don't know yet whether the burning flame that just disrupts the type 1a supernova is always subsonic, or whether at some point it becomes supersonic. So this is a deflagration, namely, versus delayed detonation scenario. And here again, nucleosynthesis calculations made predict different abundance yields and different abundance pattern. And here again, if you can really constrain on, let's say, a given type 1a supernova, the abundances, let's say, for example, nickel over iron ratio here, you will be able to discriminate between different models and provide more information and constrain, for example, the nature of type 1a progenitors or of the physics of their explosion. So this is actually quite nice. Unfortunately, this is difficult to do in practice because we don't really know that many supernovae remnants. It's not that easy to constrain their abundances directly, but we're going to come back to that later. So there's also the asymptotic giant branch stars, which are called AGBs, which essentially produce carbon and nitrogen. I won't go too much into details, but these are basically intermediate mass stars, which are not exploding yet as a supernova. They are just having a swollen envelope and just produce a lot of stellar winds in which you have a lot of carbon and nitrogen that just enrich their surroundings. And finally, as you probably know, when LIGO just detected a merger between neutron stars, now we think we start to know that these neutron star mergers actually produce some very, very heavy elements like silver, gold, etc. So in a nutshell, this is basically the Mendeleev table with, for each element, like all the origins of all the origins of each element. And of course, you all know this very beautiful quote from Carl Sagan that we're all made of star stuff, and which I still find completely amazing. All right, let's just put these stars and supernovae in the fridge for a minute, and let's now just zoom out to the larger scales of our universe, and let's look at what we call galaxy clusters. And this is what you can see on this picture here. So this is what you see optically, and what you immediately notice from galaxy clusters is that the galaxies are not so much like our Milky Way. They are so-called red and dead, so they have a lot of low mass star population. They don't really have all these big blue OB massive stars, let's say. And also in most of these galaxy clusters, you have in the center what we call brightest cluster of galaxy, or BCG, which is a very big red-ended, again, galaxy here. And now if you look at it in X-rays, you won't observe the same thing. What you will observe is a very, very diffuse and extended emission, but which does not trace necessarily all the galaxies individually. We know today that this is the intra-cluster medium. So this corresponds to a very, very hot and tenuous plasma, which is also optically thin, and which is also in collisional ionization equilibrium, which means that the rate of ionization is equivalent to the rate of recombination. And that is very, very practical in our case, because that allows us to model its spectral shape quite accurately. If you wonder why we care about this gas, I can just tell you that this accounts for roughly 80% of the total baryonic matter in a cluster, which is quite a large amount. So if you really want to understand how our baryonic matter forms and grows through the history of the universe, we need to understand these intra-cluster medium components. Just a quick slide here to show you that this is also the case, not only in clusters, but also in groups of galaxies, and even on elliptical galaxies. So you can see here, I really like this picture by the Fornax cluster here, where you see that, for example, this hot atmosphere is also found surrounding individual massive elliptical galaxies. This is another famous example here. Another thing I would like to introduce is the concept of cool core versus non-cool core systems. So if you just look at clusters in X-rays, some of them have actually a significant drop in temperature towards the center, which also corresponds to a clear X-ray peak, a peak that you see in the X-ray brightness, which is not always the case. So for example, for the coma cluster, you see that the X-ray brightness is much more extended, and you do not see a temperature drop here. And the difference between the two is mainly as attributed to the dynamical states of your cluster. So in the case of cool core clusters, the cluster has had time to cool. So basically it's dynamically relaxed, while in the case of coma, for example, it has encountered more recent merging events, etc. All right, and here comes actually one of the most central points of this talk, which is that more than 45 years ago, 46 if I count well, Ariel 5 made a beautiful discovery, which is shown here. So this is the first spectrum of the Perseus cluster. And what you see is a bump around 7 keV, more or less. And this bump corresponds to the K-shell transition of iron. And this basically shows you that not only this gas has a thermal origin, but also that it contains iron. And if it contains iron, of course, it can just contain a lot of metals in general, which is something extraordinary, because it means that the elemental building blocks of life are also found even at the larger scales of the universe. Obviously, today we have much better satellite mission to probe this, and this is, for example, the case for XMM-Newton. So if you look at epic spectra, this is typically the kind of spectrum you can find here. You can see the beautiful iron K line here, for example, but you can also see the lines of other elements here. So it doesn't look that convincing if I show you such a plot. But if I, for example, if I subtract the continuum, if I start to stack a lot of the spectra, this is typically what I find. So you see really like a lot of lines which are well identified. And if I zoom, for example, on this part, essentially this bump here, which is not one line, but it's a complex of different lines which are not resolved by the EPIC camera, by this CCD-like resolution. I can actually try to disentangle these lines if I look, for example, with RGS. So RGS, which is this other instrument on XMM-Newton, a slitless grating spectrometer. So if my source is not too extended, then I can hope to disentangle some of this line here. And again, with these lines, well, we can, as I'm going to show you in the next slide, we can constrain the abundances. Obviously, now Hitomi came in 2016 and just delivered a beautiful spectrum of the Perseus cluster. So it's the only cluster Hitomi could look at, but the quantity of information which is there is absolutely extraordinary. And I can just show you here by zooming, for example, on this region. You can see the exquisite spectral resolution that Hitomi was able to achieve compared to rate, which is actually the XMM-Newton epic resolution here. All right, so yeah, basically how does it work? Well, you just have your cluster as you see through your X-ray mission, and you can just extract any region of your choice. So I take this one, for example, and you can just fit it with your favorite plasma emission model. So you can use either the APEC model in XSpec. I personally like to use specs here, so I'm going to refer to that code instead. You can also look at RGS. So RGS, you don't have the control on which region you can probe, because it's always like a grating spectrometer with a precise region here. And yeah, you can basically do the same. And that's how you can basically constrain your abundances as free parameters if you have enough counts. So if I just come back to this Mernier table, yeah, as I told you, this means that we are all made of star stuff, and these star stuff are present at the largest scales of the universe, which for me is, yeah, it's really, really remarkable. And that might be perhaps one of the main, take-home messages of this talk. So in this talk, actually, we're just going to focus on elements from carbon to nickel, because these are those that you can see sorry, in clusters, in groups, in ellipticals, in the X-ray bands. All right. So we know that actually these clusters, these groups, these elliptical galaxies are enriched with metals. And so, yeah, this is actually the results of billions and billions of supernovae that have just exploded and that have just released their materials there. And this material is now trapped in the gravitational potential well of this system. So in a sense, what we're actually looking at is as a sort of signature of signature imprint of the enrichment of the universe, which is really remarkable. And now, of course, the questions we would like to address is where, when, and how did these large-scale structures become chemically enriched? And there are many ways we can answer this question. Of course, the most obvious one that would come to our mind is to look at redshifts, the redshift evolution. I'm going to show later that this is actually quite complicated. But we can do many other things. We can look at the spatial distribution of metals. We can look at the comparison between in metals between clusters and groups. We can look at not only the overall metallicity, but abundance ratios. And we can also look at the metal budget. And I'm going to tackle this in the next slide. So let's first look at the spatial metal distribution. First of all, I think it's important here to introduce some concepts. So for example, the concept of R500, which is the radius within which the mass density of your gas is actually 500 times the critical density of the universe. You can also define R200 in the same way here. And yeah, these are just, sorry, just two examples of simulated cluster and observed cluster here. And you can somehow arbitrarily define what you call the core region and all the outskirts, or all the regions which are close to this radii, which are actually roughly corresponding to the viral radius of your system. And this is typically for, at least for cool core clusters, this is typically a summary of most of the observations that you can find. So just the iron abundance or metallicity versus radius here. And you observe like interesting features. First, we can focus on the outskirts here. And what you see in the outskirts is that your abundance drop, of course, but they do not drop to zero. Instead, they remain remarkably flat, really uniform from, let's say, 0.3 to, well, down to up to almost the viral radius, which is quite remarkable, quite intriguing, actually. And this corresponds to, this was also shown by simulations and well reproduced by simulation, providing that in your simulation, you include a strong feedback from supermassive black holes very early on, actually even earlier than when your cluster started to form and grow. And so today, this is actually one of the best evidence we have for what we call the early enrichment scenario, in which we believe that what happened is that clusters became chemically enriched even before they started to assemble. So in individual galaxies, the metals were actually released thanks to AGN feedback, thanks to supermassive black hole feedback, and also a little bit via galactic winds. So yeah, around redshift 2 or 3, so more than 10 gig years ago. So exactly, actually, at the epoch where the star formation was at its cosmic dawn, at its cosmic noon, sorry, and also when the black hole activity was at its maximum activity as well. So now if we just focus on the core here, what you observe is, of course, that you have a central increase of metallicity here. And this metallicity actually mostly traces the iron abundance. And this is something that we find in cool core clusters, as I show you here. But also in non-cool core cluster, what you see is that this increase is slightly less pronounced, actually. And when you look at this kind of makes sense at first glance, because in cool core cluster, we have this BCG, so this huge elliptical galaxy here, which of course contains a lot of low mass stars. So presumably a lot of white dwarfs as well. And first, it was actually interpreted as a sort of delayed enrichment coming from type 1a supernovae, which would make sense. But I'm going to show you that this is actually, maybe the real interpretation is a bit more complicated than this. And yeah, I'm just going to come back to that in a few slides. Second, we can just look at clusters versus groups in terms of metallicity. And this is kind of important because clusters form hierarchy. They form from ellipticals, which themselves form into groups, which eventually become clusters. So it's quite important actually to look back in groups and also in ellipticals and see whether we find the same level of enrichment or something different. And this is actually, well, a lot of previous observations were actually nicely summarized in this plot here, where you have in the y-axis the metallicity, and on the x-axis you have the temperature of the system, which is a good proxy for the mass, in the sense that rich clusters will be usually hot, while poor groups and ellipticals are usually quite cool and are more like on the left, sorry, of these plots. So what you see is that the general trend was that for clusters, you have a more or less a flat trend, or even like a slightly decreasing trend here. While for groups and ellipticals, the less massive is your group, the less enriched would be your system actually. So these were like previous observations, but the problem is that they did not match at all what theoretical expectations would predict. So if you look, for example, at semi-elliptical models, they would predict that you would have as much iron in groups and in ellipticals as you would have in rich and massive clusters. But more recently, what we did is that we just took the latest specs version, which was actually updated thanks to the beautiful results of Hitomi, which really allowed a new update in the spectral code and so on. And we just took like a sample of clusters and groups and ellipticals with XMM-Newton, and we just redid this exercise. And this time with this updated version, we found that on average, groups, ellipticals, and clusters are similarly enriched, which also matches really well the simulations, as you can see here in red. Of course, you have a lot of scatter because each cluster or each group has its own chemical history. But you see that on average, you don't really have a clear trend here. That you can also see that's the difference between spectral codes for groups and for clusters in this plot here. Let's talk now about chemical composition, which is also something extremely important. So of course, when you look at the metallicity, you're tracing mostly iron, but you also have plenty of other elements in your ICM. And so quite earlier, when you looked at XMM-Newton with a previous version of specs or even XSpec actually, you would obtain a sort of pattern like this one. So if you just look at a sample of clusters with XMM-Newton, you would look at this, and you see that your abundance ratios are quite close to the solar ratios here, except for elements such as manganese, nickel, etc. But then Hitomi came, and Hitomi was completely revolutionizing here because it looked at the Perseus cluster with exquisite spectral resolution, plus, as I told you, specs and also APEC, the APEC model, were actually updated to really match much better the observation that we saw. And what Hitomi found is that all these ratios are remarkably similar to the solar ratios. There's also a very nice other study showing that for the Perseus cluster with both Hitomi and XMM-Newton RGS, just completing here the alpha alpha ratios. And now motivated by this, what we did was also to take the same sample as previously. So, but with the spectral resolution of XMM-Newton, and then just to apply the updated spectral codes, and ta-da, we just obtain something that's also remarkably similar to what Hitomi found, which is actually pretty encouraging. So it really shows that all these ratios are consistent, and also all these ratios are remarkably similar with the solar chemical composition. So I'm going to come back to that in a while. But this is actually very, very interesting, because what we can also do is that, so this is, for example, the best measurement of Perseus that we can say. And if you remember what I said in the introduction, I told you that, if you just take type 1a and core collapse models, and if you just compare them to, let's say, some type 1a or some core collapse, you can actually hope to constrain the physics or the nature of the progenitors and so on and so on. Of course, it's difficult to do like with different, individuals, type 1as and core collapse supernovae. But if you remember what I said, in the intra-cluster medium, basically the metals that you see are the results of billions and billions of supernovae that just completely accumulated over time. So you can't dream of a better sample here to really, to basically constrain this model. So what you can do is that you can basically take your best measurements in the intra-cluster medium and just try different combinations of core collapse plus type 1a combinations of models, and then try to see from just a basic fit which one is constraining the observations the best, and then you can hope to reconstrain the physics of this stellar systems here. And so if I do that here, for example, this is typically what we can get. So this is from a very nice paper by Aurora Simonescu. And so you can see that the best model, for example, would be a model where I have an initial metallicity of 0.02, so typically solar metallicity here, with a salpeter IMF, and I have here a deflagration model for type 1a supernovae. And of course, you can just apply different other combinations. You see that they fit the data a bit less. Another thing I can say here is that in this fit, the only free parameter is actually the ratio of type 1a versus the total number of supernovae that you have. And that's basically how it affects your fits here. But what you see is that actually none of these models is really perfect to the data. And if you look specifically on the sulfur over argon ratio, you see that all the models systematically over-predict this ratio here. So this is actually a good hint that we might still be missing something in the nucleosynthesis calculations as we have now. What we may also wonder is whether the chemical composition is the same for clusters. So as I show you, the chemical composition of clusters is very close to the chemical composition of our own solar system. And we may wonder whether this is the case for groups and for ellipticals as well. And what I show you here on these results is that it seems to be kind of the same, indeed. Of course, if you just look at groups and ellipticals, our error bar starts to be larger because it's less easy to constrain all these abundances here. But really, like if you really take this alpha over iron element ratios, the trends seem to be flat. And what we have done also recently is look at very, very deep data of one single elliptical galaxy, so something that would be really much at the left of this plot here, and just look at its chemical composition, at all its ratio here. So again over iron, and again you see that everything is pretty close to solar here, and nicely consistent with what we find in the hotter ICM of clusters. So it seems that the chemical composition does not depend on the mass of the system. Something else we can ask about, well, which is kind of related to the chemical composition, is the following. So I showed you sort of this plot, which just shows you the central peak of iron. And I explained to you that this was mainly attributed to this delayed type 1a enrichments in the core, probably from the BCG. And now we may wonder whether we have the same with alpha elements, so elements which are actually created not by type 1a, but by core collapse supernovae. And if we do that, surprise, surprise, we find that indeed we have exactly the same peak appearing here. And if you start to just look at the ratios, or if you do like actually something a little bit more sophisticated, which is just like fitting all the ratios you can have for different spatial bins. So like the exercise I showed you before, but like for different radial bins. And if you just assume different combinations of models, let's say, you obtain that the fraction of type 1a over the total number of supernovae is remarkably similar in the core. Here in this, the study does not go really far away in the outskirts, but there are other studies, for example, with Suzaku, showing that you can go quite far, and indeed your type 1a contribution, your relative contribution of type 1 remains remarkably flat, which is very, very intriguing, because it means that after all, perhaps this central iron peak may not be due to delayed type 1a supernovae, because otherwise we would not see this core collapse product peaking also in the core, since as I told you earlier, there are no recent massive stars, big OB stars. So all these galaxies are red and dead actually. If I just go back to this, to our friend NGC 1404, we can do the same sort of exercise. And then you see that, for example, for magnesium over iron ratio, we remain remarkably flat, as expected for clusters. Results are a bit more difficult to interpret in terms of silicon over iron ratio. I don't have time to discuss this further, but of course, I'll be happy to discuss that further with you if you have any questions about that. And finally, let's look at the metal budget. So the metal budget, what is it exactly? Well, this can be somehow synthesized in this quantity, which we call sometimes the iron yield. So the iron yield is basically the ratio between the iron mass that is locked in stars and in the ACM versus the mass of the gas that eventually went into stars before the stars started to lose some material by stars. So basically, this really shows you, this really represents the amount of iron, let's say in this case, that is eventually produced versus the amount of iron that could have been produced by the stars that you actually see. And so what you see here is that this value here is basically what you expect, the amount of iron you expect to be produced by supernovae. And actually, you see that for clusters, so for groups, it works quite well, but you see that for clusters, we clearly have an excess. So it seems that we observe too much iron in clusters hot gas compared to what could be reasonably produced by stars in clusters. So this is called sometimes the metal conundrum. This is something that is still not really well understood, but I'm going to show you some interpretation a bit later on. And if I go back to NGC 1404, you can try to do the same sort of exercise, and then quite interestingly, you find the opposite situation. So you find that if you go up to a certain radius, which is like the limit of the galaxy, the mass of iron and magnesium that you have in the hot gas of that galaxy is much, much lower than what could have been produced by type 1As, by stellar winds, and perhaps even by a core collapse supernovae. So it seems to be an opposite effect there. And so it might be that this galaxy has released already a lot of metals in the intra-cluster medium. All right, so let's summarize what we have so far. So it seems that the chemical enrichment at large scales has different characteristics, but basically it's especially uniform, especially if you look at the outskirts. So it's really have this remarkably uniform trend, especially here, which I told you is, according to simulations, the best evidence we have so far towards a scenario of early enrichment, so where the hot gas was enriched even before clusters started to form. The chemical enrichment is also invariant with system mass. So no matter whether you look at clusters or groups or ellipticals, you should not expect to see any notable change in their metallicity. Even more interestingly, it's invariant in chemical composition. So this chemical composition is remarkably close to solar, which is already something very intriguing, actually, that I'd be happy to discuss further. But also, this does not change with radius nor with mass either. So it seems that no matter where you look at, in clusters, in groups, no matter which radius, you're always having a chemical composition really close to solar. And finally, as I just explained you, it's very difficult to explain how iron could have been produced in massive clusters from their current stellar population. And again, this might also point towards a scenario of early enrichment in which the stellar population you see today in clusters has, actually quite very little to do with iron that could have been produced, for example, by a previous generation of stars. So maybe not population 3 stars, but maybe something a little bit in between, much earlier in the cosmic history. And so yes, all these indirect hints really point towards the fact that chemical enrichment must have occurred really early on, around redshift 2 or 3. And then, of course, what we want to do now is really to have a decisive evidence about that, right? And to really be able to look at redshift of clusters of redshift 2 or 3, and see whether we find indeed an increase with decreasing redshift or not. And this plot is really nice because it shows you basically the best of what we can do so far. And what it also shows you is that it's indeed compatible with no evolution from redshift 0 to redshift 1, which is kind of what we would expect. But you also see that the orbitals are actually very large, no matter if you just look at the core, at intermediate radii, or in the outskirts. And this is kind of understandable because if you look at redshift 1 clusters, well, you have much less photons, obviously. So it's much more difficult to constrain your, let's say, your iron line that you have at 6 or 7 keV. And you probably see where I will go. Well, I will bring you to this with this argument. So let's first talk about XRISM. So XRISM will be released very, very soon, I think in principle in 1 year from now. And XRISM will be extremely important because it will really be able to routinely make spectra with the resolution of Hitomi. So this is basically a reflight of Hitomi with, of course, the fact that XRISM will reveal also the iron L complex, while Hitomi had a gate valve which was closed on that time. So that will be extremely important first to constrain the abundances really well in clusters, in groups, in very nearby systems actually. And in that respect, it will be very, very important to actually match this with first atomic codes, because as I explained you briefly, this work was done for Hitomi, at least for the iron K complex, but with the iron L complex, so this one here, which will be really disentangled at exquisite resolution for the first time, we will really be able to improve our atomic codes here and see whether it makes some difference or not. And we'll also hope to have some improvement on the nucleosynthesis yields. So to have better constraints on these ratios I showed you before, and to really see in collaboration with theoreticians, where is the physics that might be missing to improve these yields and understand better stars and supernovae. And of course, well, we're all expecting, I guess you're all expecting that I talk about Athena. And Athena, I think this is not a surprise, but Athena will be a truly game changer in these fields. And the reason is that, of course, it has the Xi-Fu, which has a spectral resolution, which is even better than XRISM. But also, well, as you all know, of course, we have 2 orders of magnitude better effective area than XRISM, and 1 order of magnitude better than XMM-Newton, which makes it the perfect mission to explore higher redshifts. I will come to that in a moment, but first I just would like to emphasize here the fact that what you can also do with Athena is just look at nearby clusters, and you will be able to constrain many more elements, and also at unprecedented unprecedented accuracy. And for example, you can have constraints on carbon and nitrogen, which currently are very difficult to measure. And carbon and nitrogen, as I told you, they are basically coming from AGB stars. So meaning that Athena will completely open a new window in this field, because it will also allow us to look at the contribution of AGB stars in this entire chemical enrichment picture. So we will see, for example, whether AGB stars were enriched at the same time as type 1a and supernovae products or not, etc. We'll have excellent constraint on alpha elements as well. And alpha elements are very, very important if we want to really tackle this initial mass function and constrain the initial mass function. So today, the constraints are very, very difficult to obtain. But with Athena, we really hope to know, for example, whether the initial mass function of the stellar population responsible for the enrichment was rather salpeter or, let's say, top heavy, etc. And that will be very, very important to basically to tackle a long-standing debate on the universality of the initial mass function. Something else is, of course, you can also have a new constraint now on sodium and aluminum, which has not been observed yet. This is very important if you want to look at initial metallicities of core collapse progenitors. And finally, we'll have even better constraints on manganese and nickel, which are super important if you want to better understand the explosion physics of type 1a, but also the nature of the progenitor. So whether it's single degenerate or double degenerate, which is still a very hot topic among type 1a scientists nowadays. On the right plot, what you can see is just made from an Athena study where in the black arrow just shows you input type 1a plus core collapse combination yields that we actually put as an input in a simulated cluster. And we observe this cluster with mock Athena observations. And then we just fit all this we just try to recover all these abundance ratios and try to refit this type 1a plus core collapse combination among a lot of other possible combinations here. And what you see is that in terms of reduced chi-square, so in terms of quality of fit, we are very, very close to recover really well the how can I say, the right input combination of type 1a versus core collapse supernova here. So Athena will be very, very good for that. And of course, as I told you, Athena will be the perfect mission to look at high redshift systems. And so this is basically how XIFU will be able to map redshift 1 cluster. But if you look at this plot, I hope that this will definitely convince you how Athena will be a game changer here. Because with Chandra or with XMM-Newton, at redshift 1, the best we can do is barely resolve the iron K line here. But you see that with Athena, you will be able not only to superbly resolve the iron K line, but also to have access to many other elements. So you can not only look at the evolution of global metallicity of iron, but you will also be able to look at the evolution of oxygen, of neon, of magnesium, etc., and really trace back whether the evolution of these different sources of enrichment was universal, really happened at the same time, or whether there's sort of a differential evolution here. Finally, I just would like to point out that I've been talking a lot about XIFU here, and XIFU will be really, really important and really determining for this kind of science. But WFI may be very useful as well, and especially if you look at high redshift groups, because in the case of high redshift groups, what you have is that, of course, if you just look at higher and higher redshift, your signal becomes less and less strong. And so at some point, you will be forced to rebin somehow your spectra. So you will be forced to decrease your spectral resolution. And for high redshift groups, so for redshift 1 here, you see that the spectral information you have with XIFU becomes very comparable with the spectral information you have with WFI. So both instruments will do an equally good job there. But of course, with WFI, your field of view is much bigger, right? So you can hope to probe different groups at the same time. So so it's also very, very important for WFI science is very important for WFI as well. And I think I will stop here. So just with with my last take-home messages, which is that, of course, metals are found not only in our galaxy, not only around stars and in other galaxies, but also between galaxies, so really at the larger scales of the universe. All the hints we have right now really point towards an enrichment that happened early on, so more than 10 gig years ago. And one determining parameter here is the fact that supermassive black hole feedback seem to be absolutely essential for that to have happened. And yeah, this is the clues are just the fact that everything seems to be remarkably uniform, especially with system mass and chemical composition, etc., etc. But of course, we really would like to confirm this picture, not only to confirm this picture, also to find more key questions as I've addressed in this talk. But yeah, this direct evidence will be revealed by future mission, and in particular with Athena. So I think I will stop here. I hope that I have convinced you that, yeah, Athena will be essential for this science. And yes, I will be happy to take any questions.
Excellent. Thank you very much, François, for a really interesting talk. I can see that we've already got a hand up from one of our panelists, so I'll move over and let Matteo ask a question in a second. But just to remind everybody that you're very welcome to submit questions through the Q&A button at the bottom of your Zoom. So please do type something in there if there's something you want to ask. But Matteo, you can ask your question now if you want.
Thank you, François. A very interesting talk. Of course, it was easy to convince me, but I think it was convincing for everybody in the audience. I have a question on metal enrichment in galaxies. So when metal enrichment for galaxies in the local universe happened, because if metal enrichment happened in individual galaxies very early in the universe, so zeta larger than 3, and then at some point, the AGN feedback brought all these metals in the intergroup and intra-cluster medium, one might expect that galaxy became metal-starved, and then we should see now a substantial population of metal-starved galaxies. And so related to this question, how far we will be able with Athena to measure metallicity directly in individual galaxies to address this question, if it is a question?
Yes, thanks, Matteo. Very interesting question. The short answer is that I don't know. Actually, no, let me just elaborate a bit more. This is actually a super critical question here. Sadly, as far as I know, I don't think there are any studies having shown already how far we can go with Athena to really probe the chemical enrichment of individual galaxies. I do remember we did some very dirty estimates some time ago, and I do remember that we can hope to go to redshifts 1, 1.5, perhaps even 2 if we have very, very good exposures. More will be difficult. Of course, there's also, well, this is valid for clusters as well. But one of the main limitations might also be not coming from the instrument, but also from the gas itself, because it might be possible that at redshift 3, for example, your gas is not even shining yet in X-rays, and then you will probably need to probe metals through another facility, other wavelength, etc. That's the first part of the answer. I would say the second part, which is which is really intriguing. We need to find a sort of cosmic time that is that is actually suitable for galaxies to have the metals they have today, right? And for example, what I haven't really shown in details, that even in galaxies, you have this central peak there. And as you explained, if you have strong AGN feedbacks really early on, you would not really expect much to have all these metals retained. To that, I think what will be also very important in the future will be observations, of course, but so with GWST on stars, on the cold gas as well, but also simulations. I think simulations here will be super important to pick this epoch that could be the best to know what kind of feedback with AGN would be good to conciliate all the views. So I guess I'm not really a simulator myself. I guess right now the most difficult is to deal with this subgrid physics issue, but yeah, that will be definitely an improvement we need to have.
Thank you.
Okay, so I can see we've got a couple of questions in the Q&A. So I'll ask one of those, and then I'll go to Didier on the panel, who also wants to ask a question. But before I do that, so there's a question about manganese abundance. So the question is, on manganese abundance, the large uncertainty on one of the Hitomi related slides. So I think this was one of the slides where you had the distributions for all the different metals.
Yes.
Is the large uncertainty for manganese due to the uncertainty in the individual measurements from the spectral fit, or to do with a large spread of abundances in the 44 clusters in the study? So I don't know whether you can. Yes, that one. Yeah.
Yes, exactly. Yeah, that's a very good question. Yeah, so actually what happened for this plot, and especially these blue error bars, is that this is what we try to do in that study is to match what we can have with both epic MOS and with epic PN. And we wanted to be very conservative here. And what we find for all these abundances is that, well, at least from magnesium to chromium and then nickel, that MOS and PN measurements agreed really well, except for manganese. And for manganese, what happens is that if I remember correctly, I think MOS measurement is nicely consistent with one, with an error bar which is comparable, I think, to that of chromium or even calcium. But then for PN, for some reason, then you have measurement which is like extremely high. So here we wanted to be conservative and just put like draw a very large error bar here, which of course is not really Gaussian, right? I mean, it doesn't mean that the most likely value is here with a 68 probability here. I would be tempted to trust MOS, which actually really goes with the, well, it's really in line with these other measurements, but you know, I guess it's good to be kind of honest and also report that, yeah, PN was pretty high here. And to be honest, I don't really understand why, so.
Okay, thanks. Didier, do you want to go next?
Thank you, François, for a wonderful talk. I have a non-expert question for you. At some point, you said that nucleosynthesis models have also some uncertainties, or they may not be yet to the stage where we can draw definite conclusions by comparing with the data. So, I mean, is this something that is being to be worked out for XRISM? I mean, are you aware of some efforts in that direction? And what are the prospects of getting those models improved on the time scale of XRISM data, for instance?
So yeah, also a very good question. I do not know, I'm not aware of all the prospects on all the different research groups, but I know that in the case of Nomoto-san group in IPMU in Tokyo, they're actually following, they were actually actively following what happens with Hitomi already. And I think they are on to improving their models constantly. These people that are really, really good in modeling type 1a and core collapse supernovae. One thing that I can mention, for example, one recent achievement was on the electron capture rate of type 1a supernovae, which was apparently, if I remember correctly, was modeled in a simplistic way some years ago, and now they provide much more physical details, and that kind of changed actually the different yields. So I don't know exactly like what would be the next step on which exact physical details they would need to be worked on, but I can assure you that yes, research groups, at the very least one, but I'm pretty sure that many research groups are very well aware of that and will be willing to work on that with XRISM.
Thank you. Congratulations.
Okay, so there's another question from the Q&A, which is, in some of your plots, you were showing abundances as a function of galaxy cluster temperature. And so the question is just about how you're measuring the mean temperature in that situation, whether it's the mean temperature within R500 or whether it's emission measure weighted or some other way of doing it.
I do believe it's this plot, right? There are actually two plots. This one is a compilation from the literature. And from what I remember, what the authors did is that obviously each author just took different radii. So what they did is that they tried to homogenize all these different radii by assuming a sort of standard abundance radial profile. In our case, what we did is that we just tried to well, to look at all this data within some radii, which is like 0.1 of 500. This radius is a sort of good compromise between being quite large in terms of extraction region with XMM-Newton, so that you just avoid all background contamination, etc. But also being able to probe what's happening in terms of simulations, because simulations also have a limited resolution there. So this is still what's happening in the center. So here in this plot, you're still probing the different peaks, and that's probably also why you have a lot of scatter. Yeah, I think if I show you one of these previous plots, which is I believe this one here, you also see that in the outskirts you have much less scatter than what you have in the center. So in the central peak, you might have actually a lot of scatter. Today, I'm not sure we really understand why some clusters have just a moderate peak and why some have like a very, very high abundance peak. I think we may have some idea. This might come perhaps from the mass of the BCG, but again, we don't really know exactly where this peak forms. So there are probably room for the studies about that. Yeah.
François, I think part of the question was also about the mean temperature, if that was determined within.
Sorry, Thomas. Yeah, sorry, I completely forgot about that. Yes, about the mean temperature. So what we did is that you can proceed in different ways. If I just take back this this slide, so you can model your spectrum very, very simplistically and just assume one temperature, which would be truly the sort of average temperature you have in your cluster. However, this is not advised to do that, especially for groups and ellipticals, because then what happens is that you would underestimate your iron abundance. This is something called the iron bias that has been studied for quite some decades already. This is a very well-known issue. What you can do instead is, for example, model indeed different temperatures. So you can take 2 temperatures or 3 temperatures. In this study, I think what we did was to model a Gaussian distribution of temperatures, and then taking the mean temperature as, yeah, indeed the mean of the Gaussian distribution.
Okay, thanks. So I had a couple of questions. So I'll just ask one of those. So your results on the total metal budgets, where obviously you have the conundrum on cluster scales where there seem to be too much in the way of metals. Are the results that you found for NGC 1404, is that something that's seen across many systems, or is that so far just that one galaxy where you're seeing such an obvious effect in the opposite direction where you have too few weather levels?
So, yeah, thanks. Also an excellent question. So on this plot, I believe that what you see is basically clusters here, and then you go down to the scales of groups. Unless I'm mistaken, I think this plot does not include any individual elliptical galaxies. And so what we sort of try to do here is we didn't really try to put one more data point here, but yeah, also to look at the metal budget here. And what you see here, so the fact that you have actually less metals than what could have been produced by type 1a core collapse actually naturally follows the trend here, that you have a decreasing so-called iron yield with decreasing mass here. So this is kind of nicely in line with this picture here. Now, of course, one of the big questions we'd like to understand is where did all the iron from this individual galaxy, where did all the iron go? It must be somewhere. I guess it must be probably in the ICM, but where in the ICM, when, etc. I think these are questions which are quite difficult to tackle now.
Yeah, so I don't know whether you may have partially answered this already. I don't know whether cosmological simulations where you've got different feedback models and so on actually put constraints on what or give you things you can compare with in terms of what sort of mass dependence you might expect in the local universe, or whether that's not something that the simulations have tried to dig out and compare yet.
Yeah, that's a very good question, actually. I'm not so much aware of you mean with respect to this metal budget part?
Yeah, I just mean
I'm not aware of simulations really tackling this aspect. I believe, again, I'm not a simulator, so I'm not there to speak on behalf of them, but I believe that's one of the main difficulties here is again the subgrid physics, because you need to trace both what happens at stellar population scales and also at cosmological scales to really have this this formation of clusters and yeah, so to have all this accretion of gas and perhaps already processed metals, etc. So so I would be extremely curious to see whether there are indeed some predictions from simulation from there. But honestly, I don't know whether this is possible with the current simulations.
Yeah, maybe if not, then by the time Athena launches. Yes, so I don't think we have any more questions from the Q&A. I have one last one, but I don't know if anybody else has any others they want to add. I can see one or two people are starting to leave, so I'll just be quick. I just wanted to ask whether, in terms of the results on metallicity so far and all the early enrichment and so on, whether there are already good constraints on supernova 1A progenitor models, or whether really it's still fairly up in the air. I mean, in terms of the lack of delayed supernova 1A type effects, is that already telling us something important about supernova progenitors, or is it not yet constraining?
That's a very good question. A bit out of my field of expertise, actually. So from what I remember, there are like different scenarios inside the scenarios of single degenerate, double generate, etc., etc. So for example, yeah, you could imagine that don't remember exactly with detail, but you can imagine that either you have, for example, a violent merger between two white dwarfs, or that, for example, one white dwarf would be disrupted and still being somehow accreted slowly on the other. So this is, for example, part of still the double degenerate scenario. I'm not aware of all the constraints already. What I can tell you is that at least from enrichment perspectives, if I just refer back to this plot, and in particular to this study from the Hitomi collaboration, what they have shown is that it seems that you actually need a population of both single degenerate and double degenerate scenario to explain this chemical enrichment pattern here. Mm-hmm. I think indeed you can say something also about the so-called delay time distribution of type 1A. This will really tell you also a lot about after a given star formation, whether you would expect a lot of single degenerate or double degenerate, depending on when the supernova explodes eventually. I'm just not sure about how well constrained this delay time distribution is and how it can really constrain in turn the different scenario that we have.
Okay, no, that's really interesting. Yeah, go back and look at the Hitomi papers a bit more. Has anybody else got any more questions, or should we call that a day? I can't see any more hands or any more questions. No. Okay, all right. Well, thanks very much then, François, for a really interesting talk. That was really great. Thank you.
Yep. Thank you very much, Judith.